So we've seen so far that the general mechanism of aldehydes and ketones is, of course, the attack and protonate. However, let's look at the actual stereochemistry of this reaction. We're going to see that the attack step is not as simple as what we've been doing so far. That is, it's not really that the nucleophile goes underneath and attacks the carbon from below. To understand what it actually does, let's go back and look at the geometry of a typical aldehyde and ketone. Remember, the carbon within the carbonyl group is sp2 hybridized. And remember, sp2 hybridized carbons are trigonal planar. So this particular aldehyde or ketone is flat, which means the nucleophile doesn't attack from underneath, it actually attacks to the side of the carbon. Or in this case, from our perspective, to the front side. If this happens, then notice you're going to end up with this as a result after the attack step. Notice our nucleophile is attacking from the front, so in the product, it appears in the front, which means in the product, the nucleophile is coming out at us. And remember, to finish this off, after attack, we would then protonate the oxygen. And what you see in front of you is simply the product as a result of front side attack from our perspective. But notice, if our original alkene or aldehyde had two different groups, such as A and B in this example, then that means you're going to create a chiral center. Notice that carbon would have 4 different groups connected to him: the OH, the B, the A, and the new nucleophile. However, let's look at the other possibility. The nucleophile can not only attack from the front, but it can attack on the back side of this carbonyl group. If this happens, we would end up with this as a result. Notice the nucleophile is attached to the back side of that carbon. And then, of course, after our attack, we would protonate the oxygen. So, what you see in front of you is the result of the backside attack. And again, notice you would end up with a chiral carbon. The question is, how would these two molecules be related? Are they different or are they the same? Well, first notice they have the same 4 groups. Each carbon has an OH connected to it, a B, some A group, and then the nucleophile. What we want to understand here is that since carbonyls can be attacked from either side, what you end up getting is a set of enantiomers. Now, you might not see that here, but if I rearrange the product on the right and turn him around like this, you would actually see that these two compounds are mirror images of each other. Remember, that means they therefore must be enantiomers. So, what does this all mean? Let's look at a sample problem. If you're on your organic chemistry test and you're asked to predict the product of this reaction, and the exam wants you to show the actual stereochemistry, then again you would see, in this case, you have an aldehyde, you're reacting CN minus an acid, so it's probably attack and protonate. But if we're thinking stereochemistry, we know attack can happen from the front, and if that happened, we'd end up with this result right here. And of course, after attack, we would protonate the oxygen. And let's analyze our product here. Let's see if that carbon is, in this case, either R or S. Remember, we would set the priorities. OH is priority 1. The CN would be priority 2. The methyl would be priority 3. And the hydrogen would be priority 4. And what's convenient here is notice the hydrogen is in the back. So we're going to see which way this sequence turns. In this case, the sequence is turning right. So this would be the R-type carbon. But remember, that's not the only possibility. The CN can also attack from the back. If that happens, we should know that we end up getting this as a result. Our product clearly shows our CN on the back side. But let's make sure, is this product different than the one that we previously got? Well, again, setting priorities, this is priority 1, the CN is still priority 2, the methyl is 3, and the H is still 4. and in this case the sequence is turning 1 to 2, 3 to back to 1 again. But notice in this example our fourth priority group is sticking out at us, and if you remember correctly from a previous online lecture, that means you have to reverse your answer. So even though this is turning R, we reverse that, which means this carbon is actually S. So notice it is a different product. Our answer then is this right here. We get both the S and the R product. Think about this for a second. If this is on an organic chemistry test that happens to be multiple choice, then you have technically more than one possible answer for this reaction. Is it possible that we would get one product more than the other? Well, not really in this case, because both sides of the original carbonyl, that is, both front and back, are equally accessible. So you actually end up getting an equal chance of both S and R, which means that you can also say that the product of this reaction is a racemic mixture. But remember, we're only going through all this if the original problem on your exam wants you to express stereochemistry.